Welcome to this second part of our video lecture on constraint optimization, and we are discussing KKT conditions for solving the constraint optimization problem. So here is the optimization problem. We want to minimize some objective function f of x. We have g of x as equality constraint and h of x as inequality constraint. And now let's make it more general. Suppose we have g I of x and h j of x. That is, we have several equality constraints where I is equal to 1 to suppose up to m and j is equal to 1 to up to n. For example, we have a simple minimize x1 square plus x2 square subject to, I'm just writing these dummy constraints just to make you explain. This may not have proper solution. So, but let's say this is f of x, okay, the objective function. You want to minimize this, and these two are equality constraints. So you can basically write like this: g1 of x. So g1, g2 you can define like this. Similarly, you can define h1 of x. Fine. So your n here is 2 and m is also 2, right? So this is what I mean by having multiple constraints. Now what was the solution? So when you have these constraints, remember the first thing we need to do is define Lagrange, okay? And Lagrange is what? So first you write objective function, then for equality constraint, let's have Lagrange multiplier lambda times g of x, okay, plus for inequality constraint, let's have mu and then h of x, okay. Now if you have multiple equality inequality constraints, so we'll index it like this. So gi of x, for each equality constraint gi, we will use a separate Lagrange multiplier lambda I. So here will be the summation I is equal to 1 to n. Similarly, for each inequality constraint hj of x, will have a separate Lagrange multiplier mu j, and then we will have summation j is equal to 1 to n. Sorry, we have equality m, and this inequality we have n. Fine. And then what are the necessary conditions for KKT? What is the solution of this? So first thing is that you need to find this gradient of equal to 0. Now you need to find the gradient of this with respect to all partial derivatives of the components of x1, x2 up to suppose maybe xn capital, okay. And what are the further conditions for KKT? You know that one of the condition is this mu j h j of x, the product of these two is equal to 0, and mu j is non-negative. This is very important. But remember one thing, you need to first bring any problem in standard form. Standard form is this, remember this, that a function, objective function, has to be minimized. So if you have maximize f of x, it is not in the standard form. And equality constraint is obviously like this. Inequality constraint should be in this form. Let me elaborate what I mean. Suppose you have this optimization problem that maximize, again a dummy problem, may not have a proper solution. I'm maximizing this and subject to, let's say x1 plus x2 equal to suppose 4, and x1 square plus x2 square is greater than or equal to 1. Now is it in a standard form? No, we need to bring it to standard form. So to bring it into standard form, what we will do is we'll define function f of x as minus of x1 cube plus x2 cube. Because why? Because maximizing x1 cube plus x2 cube is same as minimizing minus of x1 cube plus x2 cube. So we can now write problem as minimize f of x. Now, are the constraints in standard form? Of course, x1 plus x2 is equal to 4. We can write g of x equals x1 plus x2 minus 4. What about this constraint? It is not in the standard form. So let's see if we want to bring it to standard form, how will it look like? So let's multiply minus 1 on the both sides. So we get minus x1 square minus x2 square less than or equal to minus 1. So now if you define h of x equals minus x1 square minus x2 square plus 1, now we can see that the given inequality can also be written as h of x less than or equal to 0. Now this is standard form. You see, compare it with here. The standard form is objective function should be minimized, and equality constraint is obviously there is only one way, but inequality constraint has to be in this form, h of x is less than or equal to 0. When your optimization problem is written in this standard form, then only the condition mu j is greater than or equal to 0 has to be satisfied. Suppose if you write this in another way, that is greater than or equal to 0, then the condition on mu will be reversed. That is, then you will need that mu j should be less than or equal to 0. That will become confusing for you, so you should stick to this thing. Whatever optimization problem you are given, try to bring it into this standard form, and then for every constraint, for equality constraint, bring in a separate Lagrange multiplier lambda. If there are two equality constraints, lambda 1, lambda 2. If there are three, lambda 1, lambda 2, lambda 3, so on and so forth. For every inequality constraint, bring in a separate Lagrange multiplier mu. For 2, mu 1, mu 2. For 3, mu 1, mu 2, mu 3, so on and so forth. Form a Lagrangian. Take a greater than or equal to 0. Then, mu j h j equal to 0, and also this mu j equal to 0. And one of the equations will be, that is obviously g of x equal to 0. So this also you need to solve. Fine. So this is the brief overview of KKT conditions. Don't need to go into the proofs. We have done one example. We'll do one simple example again in this second part of the video. Let's take one example where we don't have any equality constraint, only inequality constraint. Suppose we have maximize x1 x2 subject to x1 plus x2 square less than or equal to 2, and x1 greater than or equal to 0, x2 greater than or equal to 0. Let's say we have this. First thing, think about it. Is this optimization problem in the standard form? No. Why? First of all, we know that in standard form it must be a minimization problem. Here it is a maximization problem. This constraint is fine. It is less than or equal to, so we can define one constraint as h of x, h1 of x equals x1 plus x2 square minus 2. So this constraint can be written as h1 of x is less than or equal to 0. Okay. But what about these? We have two more constraints. x1 greater than or equal to 0 is same as minus x1 less than or equal to 0, and x2 greater than or equal to 0 is same as minus x2 less than or equal to 0. So we need to define h2 of x as minus x1, and so h3 of x as minus x2. We have now three constraints, and you want to maximize it, but what will be the minimization? How to write that? So you know that you need to define f of x as minus of x1 x2. Fine. Now we have standard problem. So we have minimize f of x subject to h I of x less than or equal to 0, where I is equal to 1, 2, and 3, and where f of x is defined like this, and the constraints h1 of x is defined like this, x1 plus x2 square minus 2, and the other two constraint functions are defined like this. So this should be now clear that we first need to write problem in standard form. Now next step is write Lagrangian. So Lagrangian is equal to f of x plus. Now, is there any equality constraint? No. So we will not have lambda. We reserve lambda for equality constraints. So inequality constraint, yes, mu I h I of x. How many inequality constraints you have? I is equal to 1 to 3. Okay, so mu1 h1 plus mu2 h2 plus mu3 h3. For the solution, so first of all, the gradient of L equal to 0. That is del L upon del x1 del L upon del x2 should be equal to 0. This is one equation, one set of equations. The other thing is mu j hj of x equals 0 for all j is equal to 1, 2 and 3, and mu j is greater than equal to 0. Fine. Let's now try to solve this one by one. What is the partial derivative of this Lagrange with respect to x1? So let's write first of all this Lagrange in detail here. So this is how it looks like, right? This is the f of x part, mu1 h1 of x, mu2 h2 of x, mu3 h2 of x, right? Now del L upon del x1 is minus x2 plus mu1 and minus mu2 equal to 0. What is the other equation? Del L upon del x2 is minus x1 plus 2 mu1 x2 minus mu3 equal to 0. And what are the other conditions you need to write? Mu1 h1 of x equal to 0. That is mu1 x1 plus x2 square minus 4 equal to 0. Also you have mu2 minus mu2 x1 equal to 0 minus mu3 x2 equal to 0. Now definitely we need to see several cases which will arise here. Also you have mu1 greater than equal to 0, mu2 greater than equal to 0, mu3 greater than equal to 0. Fine. Now we'll see several cases. So you have the first condition you have is mu1 x1 plus x2 square minus 4 equal to 0. This will have only two implications. So case 1, that mu1 equal to 0. Fine. Let's see what will be the solution if mu1 is 0. That is, this part is not 0 but mu1 is 0. Now if mu1 is 0, so you see you have these equations, equation 1, you have this equation 2, and then you have this equation 3, you have equation 4, and you have equation 5. Let's put mu1 equal to 0 here in this equation. So we'll get minus x2 minus mu2 equal to 0. So this gives us clearly that x2 is minus mu2. Fine. And what will be the next equation? So we put mu1 equal to 0 here. So we'll get minus x1 minus mu3 equal to 0. So again x1 is equal to minus mu3. Fine. Now we have a couple of more equations. So minus mu2 x1 equal to 0 and minus mu3 x2 equal to 0. You see what will this become? So we'll substitute this x1 is equal to mu3 and x2 is equal to mu2 in this. So we get minus mu2 times, what is x1? Minus mu3 is 0. That is mu2 mu3 is 0. This product is 0. And similarly minus mu3 x2, that also becomes same, mu2 mu3 is 0. Now this is possible only when either mu2 is 0 or mu3 is 0, right? But there is very important catch. You see, we are writing here x1 is minus mu3 and x2 is minus I think it is mu2, yeah, minus mu2. We know that we are given the constraint that x1 should be greater than equal to 0, x2 should be greater than equal to 0, right? And also KKT condition imposes that mu2 should be greater than equal to 0, mu3 should be greater than equal to 0. So if this equation is to be satisfied, the only way out it will be satisfied is that both mu2 and mu3 should be 0. Because if mu2 mu3 are not 0, they have to be positive number. Then minus of mu2 minus of mu3 will be negative, and x1 x2 will be negative, which is against the given constraint. So the only solution, if we assume mu1 is 0, is that mu2 is also 0, mu3 is also 0. Hence, what is the solution? So x1 is 0, x2 is 0 is the solution. And but this is not the optimal solution. Okay, so what is f of 0 0? So what is the value of function at 0 0? You know that function is x1 x2, so f of 0 0 is 0. Okay, and clearly we will see that it is not the minimum value of the function. Now let's look at other possibilities. Now let's move to case 2. So in case 2, just check that what was the case 1. So you assume that mu1 in this equation, mu1 times x1 plus x2 square minus 4, we assume either mu1 is 0 or this is 0. So case 1 is mu1 is 0. Now let's say case 2 that this quantity x1 plus x2 square minus 4 is 0. So then in that case, what will be the solution? Oh, before that I note that, okay, I have made a small typo mistake. It is here 2. So wherever I have written 4, it is actually 2. Anyways, it does not make much difference here, but yeah, so it is 2. Sorry. So it is not 4, it is here rather 2. So it means that x1 is equal to 2 minus x2 square. Other KKT conditions remain same, that is mu2 x1 is 0 and mu3 x2 is 0. Remember that we have these constraints already to be there. Now let's say that x1 is strictly greater than 0, okay, not equal to 0, and also we need x2 to be positive. When x1 is strictly greater than 0, not equal to 0, then this equation mu2 x1 equal to 0 will imply that mu2 is 0, okay, because x1 is not 0. That is one constraint, sorry, one Lagrange multiplier we got. Now coming back to KKT conditions, one of the equation we have is this. We can now easily solve it because mu2 is 0 and mu1 is not 0. So what we get is minus x2 plus mu1 is 0. So for this case here we got mu1 is x2. Okay. Now let's take another equation which we get from the KKT conditions is this thing, minus x1 plus 2 mu1 x2 minus mu3, this equal to 0. Now we can substitute the values. So it is minus x1. Now mu1 is equal to x2, so plus 2 x2 square minus mu3 equals 0. And x1 is 2 minus x2 square. Let's put it here. 2 minus x2 square. So it is x2 square minus 2 plus 2x2 square minus mu3 is 0. So mu3 is equal to, so 3x2 square is equal to mu3 plus 2. And definitely this quantity is strictly greater than 0. You see why? Because even if u3 is 0, mu3 is 0, then there is plus 2. mu3 you know that it is always greater than or equal to 0. So there is this 2 here, so this quantity is strictly greater than 0, means x2 is strictly greater than 0. x2 cannot be equal to 0 under these conditions. When x2 cannot be 0, so what will this equation lead to? It means that mu3 is also equal to 0. So what will be now the solution? So mu3 is also 0. So then 3x2 square is equal to 2, or x2 is plus minus root 2 by 3. And you know that x2 cannot be negative. x2 has to be greater than 0 given constraint. So the positive root only we will take x3 is equal to this. And how to get x1? For that, you know this x1 is 2 minus x2 square, so x1 is 2 minus 2 by 3, which is 6 minus 2 by 3, which is 4 by 3. So the second solution is, and what is the value of function at this point? So function is defined as x1 x1 x2. Okay, so maximum value of function in this case is 4 by 3 into root 2 by 3, which is 4 under root of 2 divided by 3 root 3. This is the maximum value under this. Similarly, you can go for one more condition, rather one more case, that is x1 equal to 0. Okay, it's a little bit tedious, but be careful. So what was the case we took here? X1 is strictly greater than 0. Look at this point. Okay, so in this case we assumed x1 is not equal to 0. Now if you take x1 is equal to 0, okay, then what will be the solution? First of all, you have x1 is equal to 2 minus x2 square. So then x2 is plus minus root 2. But again, x2 has to be greater than or equal to 0, cannot be negative. So x2 is equal to root 2 will be the acceptable solution. And in that case, 0 comma root 2 will be the solution. But let's see what will be the other conditions. Will they be satisfied? So you need to check this condition that mu2 and x1, mu2 x1 is equal to 0. But is given that x1 is 0, then mu2 cannot be 0. Mu2 cannot be 0. And what about mu3? So mu3 x2 equal to 0, but x2 is not 0. Fine. So mu3 has to be 0. And this comes back to the case 1 already solved, that is the 0 root 2 will be one more solution for this. And if you see the value of function at 0 root 2, f of 0 root 2 is 0. So this is definitely not the, we want to find maximum value, so this is not maximum value. Rather, the maximum value of function occurs at this point, 4 by 3 root 2 by 3. So this is the optimal solution. Now you see the KKT conditions are very tedious, and you should not worry about it. You will not be asked very hard questions on KKT conditions. Very simple question, very simple problems will be asked for this. By the way, in previous video we had done just one case of this problem, that is maximize x1 cube plus x2 cube. This also can be solved in the same way. I mean, you can form the KKT conditions and then take different cases. So I will summarize KKT again. You have objective function which you want to minimize. If it is maximized, just change it with minus of that. You have equality constraints, which we already know. You have inequality constraints. Then what you should first do, form the Lagrangian, which is equal to objective function plus, for every inequality there is a Lagrange multiplier. If for every constraint, sorry, there is a Lagrange multiplier. If constraint is equality constraint, then denote that by lambda, and if constraint is inequality constraint, denote that with mu. Now after forming Lagrangian, find its gradient, put equal to 0. And the other condition is this, the inequality constraint Lagrangian mu j hj, this product is equal to 0, and these mu j's have to be positive. So these equations when solved, take different cases. Suppose mu j and h of x equal to 0. So you can broadly take two cases, either mu is equal to 0 or h of x equal to 0. That is how you get different cases in KKT. So this is all about KKT, and this also ends our discussion on optimization. Now only two major things I need to share with you. One, which I have promised, it is the pandas package, how to access the data from the files. And one is the machine learning lectures. So in machine learning broadly, we'll have four small videos. One will be about linear regression, the other about logistic regression, and then definitely this forms the basis for understanding the neural network. And also we'll try to see one basic clustering technique called k-means. Okay, thank you.